Yes, good evening to everyone. So, welcome to the day 7 session on types of force fields, quantum mechanics, and conformational search. So, before going to today's session, can we recap the last session topics? So, can I ask you specifically in the last session topics like what we discussed in molecular modeling, small molecular modeling methods and types? Yeah, my first question is we have seen some tools and databases for modeling small compounds. Okay, so mention what are the tools and databases we have discussed on yesterday. First, about tools. Databases, I think you know NCBA PubChem, RuckBank, CHEMBL, CHEBI, Drug. So we have so many databases for small compounds. How about the tools? What tools did we discuss on yesterday for modeling small compounds and also for modeling peptides? Give me some software tools. Yeah, participants. I think if and if I ask you through poll, you will be answering. So why can't you try this? Tools for modeling small compounds. If the structures are not available in public domain databases, we have to construct the molecules in few tools, isn't it? What is the tool I've explained you on the last session? I told you free VAS, free open source softwares we can download and install and we can able to practice through that. Do you remember? I practiced something like Astomna fan. I have drawn the Astomna fan and we have seen related things. Very good. Only one is interacting. So actually I mentioned like for modeling protein, we can go with Swiss model. For modeling peptides, we can go with Vega or we can go with PepFold 3. Very good. Your answers are right. How about small compounds? The other participants can interact. So I opened a software and I drawn the acetaminophen structure. I searched similar compounds. I have also searched in NCBI PubChem what exactly is that compound I have drawn. What is the name? No one is coming up with a correct answer. Chem Sketch from ACD Labs. You forgot, isn't it? ACD Chem Sketch. And then I told you something like mole inspiration, mole soft. Okay, there are plenty of tools to draw the chemical compounds, including Discovery Studio Visualizer. So all these things you can able to sketch the chemical compounds. Even we can sketch the peptides. Okay, that is the Discovery Studio Visualizer is also used to sketch the peptides. Okay, and we have seen one tool for modeling RNA molecules. What is that? SimRNA server. Okay, so this is the tool for modeling RNA. What else did we discuss? So now let me go ahead with the today's session topics. So today we'll be discussing something on types of force fields, quantum mechanics, de novo drug design. Okay, so about today's contents, molecular dynamics, quantum mechanics, force fields, energy minimization, and a software called Probit Charming for energy minimization. And then we discuss on de novo drug design. Now about molecular mechanics. What is molecular mechanics? So in molecular mechanics, we have three types of subjects. One is classical mechanics, statistical mechanics, and the third is the quantum mechanics. So in classical mechanics, we simply discuss about Newton's law of motion. So most of them know about this. That is, force is the product of mass and acceleration. So this is an important Newton law of motion, isn't it? Like so, from if you throw a ball from here, how much distance it can move, or if an apple is falling from the tree, so what is the force it can able to fall down? Okay, everything we can able to determine through Newton's law of motion, isn't it? If you start like this, okay, and if you work on the molecules, in the molecule you have plenty of atoms. So in each and every atoms, okay, we can able to calculate the forces. The sum of all the forces is the total force of the molecule. This is how we can calculate it. And generally, whatever we make in classical mechanics is a macroscopic large scale data. Overall, for a protein molecule, what is the total force? And what is the force after energy minimization? So this is how we do. Okay, so actually, if you want to calculate the energy from the force, everyone know that energy is nothing but the force into distance. So how much distance it has moved and how much force we have applied. So this is how the energy is determined. Okay, even the energy of a protein molecule is defined as the force of all the atoms of an amino acid into the distance. You got it. This is how the energy is determined. Of course, we take it for macroscopic data, for example, for a protein molecule like that. Now, let me go with the statistical mechanics. So, this is a second mechanics, like unless we use the classical, then only we can go with the statistical. Statistical, the name itself implies if you take a macromolecule like a protein, we have a plenty of atoms, thousands of atoms are available. Then for each and every atom, there will be an energy, force and energy. So you can also find energy trajectories for each and every atom. If you have a 1,000 amino acid protein, I mean 100 amino acid protein and 1,000 atoms are approximately for each and every atom, you can find this kind of energy versus probability. Okay, so together we take all the 1,000 atoms and then we can see. So here the scale is mesoscopic. Okay, so we take many particles in consideration. For example, atoms packed inside the gaseous molecules packed inside the cylinder. Then how many molecules are there in the cylinder? So like this, if we go with the statistics, probability calculation, we call it as statistical mechanics. The third is the quantum mechanics. If you want to link all these three comes under biophysics. Whatever we studied in physics, if you apply to the biomolecule, then that's what we call it as biophysics. In drug design, whatever software tools are developed and whatever we are using, including Discovery Studio Visualizer, this PDB, RASMOL, so many visualizers we have discussed, isn't it? In all these visualizers, obviously we are using these kind of biophysics. In this the third category called quantum mechanics. Okay, this is an advanced study. In this quantum mechanics, we study the effect of photon. Okay, on energy levels. How we study the effect of photon? What is photon? Photon is nothing but a light particle, isn't it? If a light particle is going to, if you have new, uh, and I mean, electrons are rotating in an orbit, and if you have a nucleus, we have protons and neutrons inside. And if you, in the electron is hit by a photon, for example, if an electron present in the orbit is hit by the photon, what is photon? Again, I'm telling you, it is a light particle. What is going to happen? The electron is going to excite, isn't it? So the photon can hit the electron to go with the excitation and emission kind of wavelengths. Where exactly we can use this kind of a concept, if you want to determine absorbance of a protein, I mean weight of a protein, the weight of a protein can be determined through instruments like spectrometers, UV spectrophotometers. What exactly we do in UV spectrophotometer? We take a sample, can be a protein sample in a cuvette, and then we pass the light. So in the transparent cuvette region, the light passes and hits the kind of sample. Then obviously we can able to find absorbance is measured. Like spectrophotometer, we also have the fluorescence spectrophotometer. So if you want to measure fluorescence, even we can able to measure through that. Obviously, here also you have the same principle. Like whatever we pass the light, photons from the light is going to hit the protein sample, and obviously whatever electrons you get the excitation emission that can be measured here. So whatever we use in analytical laboratory like spectrophotometer, calorimeter, nephelometer, turbidometer, everything operates based on these principles. And here the quantum, the name itself implies quantum is what? Light. The light is going to excite the atoms with the energy, and this can be measured. So here we can able to see we are measuring up to the microscopic level, okay, through atomic and subatomic scales, okay, based on number of electrons present in valence and how many photons are going to hit. So based on this only the observance will be determined. So obviously, we are following the wave particle duality, means a Schrödinger wave equation. We use the generally Schrödinger wave equation to determine wave particle duality. Like for example, if a photon is going to hit an electron, the electron, okay, so is going to follow the wave-like motion. Okay, so even not only the electron, even the atoms can follow these kind of wave-like motions. Okay, so this is what we describe in this Schrödinger wave equation. Okay, one atom is considered as a one particle in simulation in software. So obviously, so one atom kind of a motions we are determining through wave particle duality through Schrödinger equation. So this is something about the quantum mechanics, which is an advanced study compared to classical and statistical mechanics. Now let me take you to the next thing, that is how to use this in drug design. In drug design, whatever we discussed as molecular docking, I mean, these are the tools for structure-based drug design, molecular docking, MD simulation, conformational analysis, binding free energy determination. This binding free energy determination we also find in both docking and MD simulations. So overall, in structure-based drug design, uses this classical mechanics, that is using F equals ma, or even it can measure the energy from the force. Okay, if this is something about classical mechanics, that is using basic physics in drug design. If you come across the statistical mechanics, this of course uses the machine learning approach, okay, which is a probabilistic method. And here the examples you can take like a QSAR modeling, which we'll be discussing on tomorrow. Quantitative structure activity relationship modeling. This is coming under ligand based drug design. So ligand based drug design, QSR modeling, ADMET prediction, virtual screening through hit prioritization, de novo drug design, whatever we will be discussing it on today. So on property predictions, everything comes under applications of the statistical mechanics. This is fast and scalable, of course. Now let me take you to the quantum mechanics applications in drug design. So you can able to see accurate binding energy calculations. Accurate binding energy calculation, how we can able to find if and if a photon hits an electron. I told you this kind of theory, isn't it? Where the atom can move in the form of a wave-like motion instead of straight linear motions. So just because of that only we can able to determine the excitation and emission kind of wavelengths also. For example, if a ligand, okay, is interacting with the receptor, then most of the ligand and receptor is a kind of a reversible reaction. That is, ligand receptor complex is formed, and this ligand receptor further can be dissociated to form ligand and receptor. Or else, if if the ligand is an enzyme, and sorry, if the so I just mentioned about ligand receptor, and if it dissociates, it form the ligand and receptor, isn't it? So, and if you see, I just erase this. I don't like to. come up with this theory now at present. I just explaining you like ligand and receptor if under if it is interacting, then it can form the ligand receptor complex. The forward reaction is measured as K1 and the reverse reaction is measured as K minus 1. So just because it's a reversible reaction, so under pH variations or under any physicochemical variations, I mean under conditions, under these conditions, the ligand receptor can be dissociated to ligand receptor. Instead of ligand receptor, if I take ligand as a substrate and receptor as an enzymatic protein, then this enzyme and substrate can react to form enzyme substrate. So for this, the forward reaction rate constant is K1 and reverse reaction constant is K minus 1. And if it is further dissociates and if the rate constant is K2, then this enzyme is released and instead of substrate, we will be getting as a product. We will be getting as a product instead of substrate. So this is a irreversible reaction in case of enzyme and substrate. So if you find the reactants are going to form the products and in between the transition state, if you want to check the energy will be like this. Okay. So we can able to find the applications in accurate binding energy calculations, reaction mechanism and transition states. Okay, so most probably we use these kind of simulations, I mean, this kind of application in hybrid simulations. For example, if you take one molecule and if you subject to phosphate buffer saline, PBS saline, what is the stability of your sample in PBS? Similarly, you can check in methanol. Similarly, you can check in water. So checking the effect of biomolecule in particular solvents. Okay, so this need even these kind of quantum mechanics calculations. Of course, we use the Schrodinger wave equation and whatever we predict through these kind of hybrid simulations is going to show you a very high accuracy kind of a data. Whatever computation we predict, that will be more that is more associated with the wet lab experiments data. Okay, this is something about the difference between the types of mechanics and how about the applications in drug design. Now, something about molecular dynamics. As I mentioned you on yesterday, in molecular mechanics, defaultly, we have two types of studies. In molecular mechanics, defaultly, we have two types of studies. One is molecular statics and another is molecular dynamics. Defaultly, whatever we study as molecular mechanics comes under molecular dynamics. So it is a computer simulation method for analyzing the physical movements of atoms and molecules. And if you see the molecular statics, that is actually a static thing, with that we don't find a movement of atoms and molecules. If you take any kind of a drug design applications, like taking a drug and checking the effect of drug for treatment of disease, it undergoes the dynamic motions. So whatever we call it as a molecular mechanics is defaultly a molecular dynamics. And if you see this molecular dynamics versus Monte Carlo, so you can able to see each and every blue color dots or nothing but atoms of a protein. Think like this is a protein, and if you see this Monte Carlo, what is going to do with this? So whatever we have an atom, see, this is actually, this can be an atom 1. This can be an atom 1, whatever we see in this blue color. But this atom can be atom number 12. Okay, the atom 12 can come closer to the atom 1. How come it is possible? Only through folding. Whatever surface we can see, this surface is going to determine the protein folding characteristics. Okay, you know, actually in protein folding, we can able to check, we can able to measure through protein reaction engineering, through the different reactions. Like we heard about something like zero order, first order, second order, third order. So whatever we have come across in chemical reaction engineering, that is equivalently applicable to the protein reaction engineering. If you want to make protein more stable, we have to do the molecular dynamics simulation, of course. And if we link with the Monte Carlo, the atoms in the correctly folded state in energy minimization protocol can fix us the more stable structure for the protein during the folding. So some proteins follow first order, some proteins follow second order. It depends. Now let me go to the next slide. This is about the main areas of MD simulations in drug design. So if you see the number one, conformational sampling, we can able to use this in applications like binding pocket detection. So actually, if we come across the binding pockets, we have two types of binding pockets. One is lipophilic binding pocket, okay, and the other is hydrophilic binding pockets. If you see a protein molecule, okay, whatever, if you see a protein molecule, whatever the, I can show you with the diagram actually. Like for example, think like this is the surface. See the surface, on the surface, okay. So whatever we have this protein, think like this is an entire protein, and if this protein, okay, you are going to encapsulate in a grid box, in a grid box. So sorry, actually I have to cover the entire thing. If I'm enclosing the entire protein in a grid box, okay, we have plenty of grid lines in a cubical box. And if I want to determine binding sites, what I can do, I can pour the water. Okay, I can pour the medium as a water, and wherever the water is going to accumulate. So this is the surface, isn't it? This is the surface region. So wherever I can able to see the water is going to accumulate, this is what I call it as hydrophilic binding sites. Hydrophilic binding sites are determined only through the uh, this kind of accumulation, and so these are present only on the surfaces. But there are some binding sites which are lipophilic. In lipophilic, the sites are buried inside. The binding sites are present in inside. Okay, so the water can't able to get inside, even if you pour water inside this cubical box. Okay, this is how we can distinguish the hydrophilic binding sites, which are generally present on the surface of protein, and lipophilic binding sites, which are buried inside the protein. So if you want to determine these kind of a pockets, multiple hydrophilic and multiple lipophilic binding sites, we can use the conformational sampling method. And number two, we can also use it for analysis of binding paths. Okay, like however we are seeing with the association with the Monte Carlo method. Okay, this can give you an analysis of binding paths and rearrangement processes. Number two, this can also be used. Okay, so whatever we call it as a molecular dynamics, a part of molecular mechanics simulation. If you see, the second thing they have mentioned is energetics. The energetics calculation is used to determine the simulation of binding and unbinding. For example, if you use a drug, how much drug is binding with the target receptor and how much is going to unbind with the exact target receptor. This can be determined through the energy determination. Okay, so this is what we can able to find. This is one of the major application to check about the binding and unbinding nature of the drug molecules. The third application of MD simulation is in determining kinetics. Kinetics, that is sampling of unbinding events, again and off of it. Okay, so these are the examples and areas of MD simulation. So quantum mechanics we already discussed thing, but we discuss now with a diagram. See, this is a support, and this is also a support. We have two molecules A and B, but in this A, okay, I just drag with a small force. So this is moving very slowly and with restricted motion from here to here. Okay, this alone we can able to see. But if I pull it with more force, you can see the molecule is moving up to this extent to this much extent. Okay, the traveling path is more here in molecule B when compared to molecule A. And similarly, if you see the wave-like motion, you can see sine wave, cos wave, tan waves, whatever we see in the trigonometric thing, you can see all these types of motions here. Okay, so like however we see an atom is linked with the support and how it's going to move. So the same kind of principles are used for simulation of protein molecules or even a ligand binding with the receptor molecules. So in docking and simulation, we use these kind of quantum mechanics. Okay, for each and every atom can be a ligand binding with receptor or receptor itself will follow this quantum-like motion. So for this Schrodinger wave equation is used. Now next thing we will be discussing on force field. So till now we discussed on quantum mechanics, and in this session mostly we see the theoretical concepts. And next session also we find much of theoretical, but the next session, that is on Wednesday, you find more than 60 to 70 percentage practical sessions. So it depends. Okay, now something we'll discuss on the theoretical concept like force field, but I also tell you like how to use this force field calculations using the tools. Now about force fields, what are force fields? So actually these are used to calculate the forces of atoms, of macromolecules or micromolecules. If you want to calculate the forces of ligands or receptors, we can use force fields. There are types of force fields. Okay, like number one is the classical force field, polarizable, reactive, force grained. Using machine learning, we can predict the force fields. And water, modified amino acids, and other methods are also available. Okay, so if you see the force fields, here I told you an example. So if you see a molecule like this, okay, if this atom is moving from here to here, whatever you can able to find is a kind of a angle, okay, angle bend. And if you find this molecule can rotate along its axis, a moment of inertia is observed, then we can measure the torsion angle. Similarly, bond stretch can also be formed. Okay, this is or used for calculating the bonding interactions. Okay, now let me discuss about the types of force fields in detail. Number one is the classical force field. What is classical force field? The name itself implies classical. That is, we calculate the forces using Newtonian law of motion. Okay, that's what we discussed in initially. So whatever discussed as classical mechanics, similarly the same concept applies. Okay, that if you use the Newton's law of motion to calculate forces, then it is classical force field. The example of tools, if you see, Amber. The expansion of Amber is assisted model building and energy refinement. This is widely used for simulation of proteins to calculate the. In simulation, one such step is force field. Simulation is a major process. We have so many sub steps. One step in simulation is force field calculation. So if you see, if you want to calculate the forces for proteins and DNA, then we can use Ampere. If that is Ampere and this is the expansion of Ampere, the next thing what we discuss is consistent force field, which is abbreviated as CFF. This is used to determine forces for organic compounds, that is for drugs, including force field for polymers and metals. Those who are studying materials engineering, they can also use the CFF. The third thing is the charm. In most of the tools, we use charm. In GROMACS, molecular talking, using Autodoc, Discovery Studio Visualizer, we use the charm method. Charm is chemistry at Harvard molecular mechanics, developed at Harvard. So we have this kind of a name, abbreviated thing, and you can able to see the applications that it is can be used for determining force field for both small molecules as well as macromolecules like 15 molecules. Okay, and the fourth one is consistent valence force field. Consistent valence force field is broadly used for small molecules as well as macromolecules. Bromos, whatever I'm showing you, amber, CFF charm, these are also examples of MD simulation softwares. I told you simulation, we find one part of a simulation is the force field. So these are nothing but a simulation softwares. Some softwares will come with a package to complete the entire simulation. Some will be a part of the simulation software. Okay. Now let me go with this. The fifth example is Gromos in classical force field. This is Groningen molecular simulation. Okay, used for proteins, nucleotides, and sugars. So used for both aqueous or non-polar, apolar kind of compounds. Interface force fields, Merck molecular force fields, optimize potential for liquid simulation. So like this, we have types of force fields in classical. Now the second force field is the polarizable force field. The name itself implies polarizable. It means that the force fields are used to calculate forces only for polar compounds. Polar compounds, I mean the compounds with hydroxyl groups. Okay, so only the compounds with hydroxyl groups, we can be able to use this force field. The examples you can see once again, you can find amber. The amber is also found in classical. This is also an example for polarizable. The next thing is amoeba. It means that atomic multipole optimized energetics for biomolecular applications. So this is a classical, this is a best example for polarizable force field. Charm is also used for calculating, this is also a polarizable force field used for calculating forces for polar molecules. And we have exclusive tool called polarizable force field. And we have CPE, CAS, PHAST, Orient, etc. Okay, now let me go to the third force field called reactive force field. The name itself implies reactive. I told you an example, isn't it, related to reaction. So instead of a ligand receptor in common thing, if you take a ligand as substrate and receptor as enzyme, then whatever it reacts, it forms the enzyme substrate complex. But after dissociating, we get like enzyme and product. The substrate can't be recovered. Only the enzyme can be recovered. What is going to happen here in the metabolic reaction, in an enzymatic reaction, the enzyme substrate dissociate as product, isn't it? This is a reaction. And for these reactions, we use this kind of reactive force field. Examples or empirical valence bond. And number two is reacts force field, reacts FF. Next force field is coarse grained. The name itself implies coarse grained. Some drug molecules are present in coarse grains. Like if you see the grain pharmaceuticals, we generally encapsulate in capsules. We can't able to make in the form of tablets. If you find the active pharmaceutical ingredient can form only the coarse grains, then we can encapsulate everything in capsules, isn't it? We generally use the hard gelatin capsules for that. For that kind of a molecules, we can use this coarse grain force field. The examples provided are dissipative particle dynamics, Martini, Syrah, and virtual atom molecular mechanics. Now, we have completed types of force fields and its applications with respect to biomolecules. The force fields are used to calculate forces for both small molecules as well as macromolecules. We also distinguish the type of tools used for determination of forces in force fields. Now, let me come across with energy minimization. If only if we calculate force, then only we can calculate energy. The energy is calculated generally through this formula, one of the major formulae. If you see this kind of energy, whatever you calculate for a macromolecule like a protein, okay, will be a maximum. If you undergo energy minimization protocol, the purpose of energy minimization is to make the protein more stable. It means that if you reduce the energy, the protein is more stable. So it means that where the protein will be in perfect folded state. Might be before energy minimization, it will be in unfolded or refolded state. So to bring a protein a more stable structure, we have to do energy minimization protocol. Similarly, it applies even for small compounds. Okay, energy minimization, or also called as energy optimization, are also called as geometry minimization or geometry optimization, which is a process of finding an arrangement in space of a collection of atoms, where according to some computational method of model of chemical bonding, the net interatomic force on each atom is acceptable close to zero. One thing you have to remember, if you do docking, modeling, simulation, in all the applications, we are using these concepts. That is calculating force fields and immediately applying the energy minimization. Under energy minimization, we have different types of energy minimization. Okay, the best methods, the best broadly classified as steepest descent energy minimization, and the next is the conjugate gradient. Steepest descent, also known as gradient descent, which is a first order optimization algorithm used to find the local minimum or maximum. Okay, more about this energy minimization. If you go with for a few more sessions, you can understand perfectly. And for the steepest descent, it uses the Laplace transformations to calculate the energy. If you see the conjugate gradient, it is an algorithm for the numerical solution of particular systems of linear equations. Okay, and this uses Cholesky decomposition. So overall, if you compare steepest descent versus conjugate gradient in energy design, okay, we can able to see that steepest descent is easy to implement and it is a robust. But if you go with the conjugate gradient, okay, so it shows a negative gradient direction, and this is a faster conversion, more efficient for large systems. For example, if you go with the energy minimization of protein, I suggest you to go with the conjugate gradient. If you go with small molecules like compounds like this, okay, the compound small molecule, small compounds like this, go with the steepest descent. So again, I'm telling you, you go with the macromolecules like proteins, we can go with the conjugate gradient, but for small molecules, we can go with steepest descent. So this is how the algorithms are developed accordingly. Now something this is actually left out in the previous force fields. I told you even with the machine learning, we can determine the force fields, I mean forces. So through force fields. So the examples provided are ANI, F flux, tensor mole. So these are the examples, okay, del ML and CHNet. So these are the machine learning algorithms used to determine the force fields. Now that is completed, entirely completed. The force fields and energy minimization is completed. Now let me take you to the next concept called Probist charming. The Probist charming is used to determine actually energy and predict the energy minimization. This is what I will be practicing it on today. So for getting inside the Probist charming, simply type the Google like Probist charming. Then we'll be getting a window like this. In this window, it asks you to upload the 4-letter PDB ID. Either upload the 4-letter PDB ID or you can upload a PDB file. So if you upload a PDB ID, it is a must to specify the chain. The chains will be like A, B, something like that. You must specify one or two chains or even one chain that should be specified. Then only it works. And of course, the email ID is optional for you. Sometimes it takes more time to generate the result. I suggest you to provide your email ID before generating it. So initially, I have given an input like this, that is 4W05. So this is the PDB ID I have given. Dot A refers to the A chain. So after giving this PDB ID and A chain, I can able to get a series of chemical compounds which can bind with the binding site 1. Actually what the probe charming is going to do, this is generally used to predict the binding sites. Not only it's going to predict the binding sites of a 3D structure of a protein, but it also checks which compounds. There are so many library of compounds deposited in probe charming. It checks which compound is going to best fit with binding sites. For example, in binding site 1, this is the best compound binding, and how we are telling which is this is best binding. This best binding is measured through confidence score. The confidence score we got is 4.47. It is progressively decreasing. All these compounds showing 4.47, it means that all the compounds show the equal binding affinity with respect to that binding site 1. Might be the binding site 1 is located in this region. If this is the binding site which I am shaded in the red region, the second region, okay, the binding site 2 region can be here also in this region. So like this, we have different binding sites. So nearly find that the binding sites information is shown here. The binding site 2 is shown here. If you click this binding site 2, we find different compounds or binding with a specific site region. So what do you understand from the probe charming? Probe charming tool is generally used to predict not only predict the binding sites, but it is also used to check which compounds are going to best fit with specific binding sites. Now, let me take you to the next application. De novo drug design. What is de novo drug design? So, de novo drug design is generally classified as atom-based construction and fragment-based construction. We have two types accordingly: structure-based, ligand-based, and of course here also structure-based, ligand-based. So whatever we discuss, ligand-based, structure-based, okay, the ligand-based like a QACR, scaffold hopping, pseudoreceptors, pharmacophore modeling, and even the structure-based, you can find the de novo drug design. Okay, whatever we're discussing as de novo drug design comes under structure-based in default, and molecular docking also comes under that. Now something about de novo drug design. What is de novo drug design? It is a computational technique wherein novel molecular structures with desired pharmacological properties are generated from the beginning or scratch. Do you understand anything? So before coming to these definitions, I directly take you to the figure and explain. Okay. So in this figure, okay, what you can able to see, there are two types of de novo drug design. One is de novo linking, the other is de novo evolution. In de novo linking, you can able to see one receptor. The receptor can be an enzyme also. Okay, in a receptor, if you find a ligand is binding, we call that as binding site. But if receptor is an enzyme, instead of binding site, we call the binding site of the ligand as active sites. The active sites are generally found in enzyme type of protein. Got it? Now, let me discuss further in de novo linking. So, if this is an receptor or an enzymatic receptor, I told you this is a ligand. This is ligand 1, this is ligand 2, this is ligand 3. What is ligand actually? A kind of a drug or inhibitor or whatever it is. So, if you have three ligands which are binding in three different positions in that particular receptor, Okay, and if each and every binding shows a significant biological activity. For example, if you take acetaminophen, you heard about this? What is this? Nothing but a paracetamol. Paracetamol is used for treatment of analgesic. It is having an analgesic property. It is also having antipyretic activity. What is analgesic? Analgesic means if you want to reduce the pain, okay, we use acetaminophen. Also, if you want to uh, avoid the high temperature, if you want to relieve from the high temperature, okay, then we are using the acetaminophen. So to relieve from pain as well as to relieve from fever, we are using this. So if this binding site is for pain, consider this binding site is for relieving from fever. Okay, and this is for another application. Then if you are having a this three different parts, for example, if you see the best example I can tell you is the acetaminophen, the paracetamol nowadays is coming along with a few more drugs. Even recently when I approached the doctor, he has given me caffeine linked with the paracetamol. I don't know how many heard about this. Caffeine linked with the paracetamol. You know why they have given the caffeine? So paracetamol, I told you, it is used for relieving from pain as well as from the fever. No doubt in that. But if any kind of persons want to be active, for example, tomorrow he has an examination, but he is suffering from fever today, the doctor can prescribe this kind of a medicine also, which is coming along with the paracetamol, because the caffeine makes your neurons more stimulative. If the caffeine can stimulate the neurons, okay, even during the fever, okay, he will be relieved from the fever, and this kind of a stimulation is sufficient enough to wake and to be active, to make active, we use that. You understand now? So if you have multiple drugs coming with a standard drugs or common drugs, we can able to link with each other. So to link drug 1, drug 2, and drug 3, we can use linkers. We can use two different linkers. Okay, the linker 1 and linker 2. Okay, the linker 1 and linker 2 is linking drug 1, drug 2, and drug 3. And finally, whatever you link like a drug 1, drug 2, drug 3, using linker like L1 and L2, this is the finally designed compound. So this concept is what we call it as de novo linking. Actually, in drug discovery hackathon competition, which happened in 2020, organized by ASD and CSAR, okay, they also had a problem statement to develop drugs under de novo link and de novo drug design. Okay, even a few students in SVC have cracked that kind of a problem statement to secure funding of around 3.6 lakhs. Now, the next thing is de novo evolution. Okay, in de novo evolution, okay, we can able to see that initially we have one drug molecule, but later on another binding site we are linking with a linker, and we are linking a second drug molecule. Now, if you want to link another molecule which is going to bind with the third binding site, then that is drug. We link again with another linker. But see the linker shape. The first linker is linking drug 1 and drug 2. The second linker, whatever we use, is linking the drug 2 and drug 3. So you can find the shape of the linker is varying, and how we generate uh, how we check from each and every drug. Okay, if this is a most important site, then we find a drug 1 is discovered initially for the binding site. Next, if another binding site is discovered, then we can come up with another drug 2. And if you find another third active site is also important, then you are coming up with a third drug, and you are linking all these three drugs. Drug 1 is linked with drug 2, drug 2 is linked with the drug 3. So this process is called de novo evolution. This is how it distinguishes with de novo linking. Now something about fragments and perfect binders. The target binding site can be in this morphology, and the hit identification, whatever we find, might be this morphology. And if you can have a fragments which can bind with almost all the binding sites, okay, then through the fragments we can link with the linkers. This is what we call it as a fragment to lead approach. To come up with a lead from the hits, we use this kind of a de novo drug design methodology. Similarly, hit to lead. So hit is this, lead is this. We attach few functional groups. We can able to say it's also binding with most of the binding site regions. So this is how the perfect binding can be attained through fragment to lead or hit to lead approach. Now these are the steps or in the methods in fragment based drug design. The first step is growing. Like see, this drug molecule is there, and now we have another drug molecule is there. We just doing the growing procedure, and number two is the linking. Okay, so under linking, we are linking through this linker. This is the linker part. This is the linker part. So first we grow, and then we link. Okay, this is the drug one actually, and this pink color is the drug two. They are just growing, and this is a linking with linker. And the third one is the merging. So in merging, you can see the cyclic ring change. So fural to the thiophene structure, cyclic structure, merging. This is what we call it as. So these are the methods and fragment-based drug design. Prediction and evaluation, de novo drug design. So whatever we discussed, okay, so that is sufficient enough. So for this, we can also use deep learning, machine learning techniques to come up with a new drugs. So what are the designs? What are the inhibitors we designed using de novo drug design? If you see the drugs like the dual acetylcholinesterase and MAO inhibitors, okay, for treating two different diseases, okay, we can link one drug with another drug. Like how I told caffeine linked with paracetamol. Okay, this was also one more example. Okay, for fragment-based drug design, we have plenty of tools. The best tool I can tell you is Scroidinger package. In Scroidinger package, we have an exclusive tools for fragment-based drug design. And one of my colleague also mentored the students to crack around 3.6 lakhs grant. I mean, the internship stipend for the students. Okay, he and his students utilize the Scroidinger package. During the Drug Discover Hackathon competition, the commercial tools are made available free for 4 months. So during that particular time, so they utilized and they have won that kind of that much amount. So if you see the computational methods for drug design, the first method is fragment positioning, site point connection, fragment connection, library construction, molecule growth, and random connections. Virtual screening can be linked with de novo drug design to come up with a base drug from multiple drugs. That's it. I completed. One thing I can show you today is the probis charming. So how to practice probis charming? Just in Google type probis charming. It leads to take to the probis server. The name itself implies charm. Okay, that is charm is a polar force field as well as classical force field. Okay, so that can be that is going to use the energy minimization protocol to determine the binding sites. Okay, now you have to upload a PDB file, and then if you have multiple chains, provide one particular chain. And if you want to select any particular binding site, you can able to select from here after uploading a file or after uploading the PDB ID. Now let me type one kind of PDB ID 1XIH. Now I'm going to type a chain A. Okay. Email ID is an optional. I'm giving my institutional email ID, clicking submit job. So now it is enqueued. If the protein structure is not in good quality, You won't get this. It tells that error found, something like that. So I, whatever PDP I have given is okay. So only it is enqueued. So you're going to get the results. Okay. So I told you how the results looks like. Okay. So I check whether I have previous results or not. Probably is finished, but it's generated on January 4th. Let me check whether I can able to open this link or not. No, before 7 months, I don't think we will be getting the result. The site can't be reached. But okay, whatever I'm going to generate today, we'll be seeing the results on tomorrow if the results are generated to my email ID. Okay, so I've completed today's session. If you have any doubts, you can ask me. Do you have any doubts? If no doubts, thank you very much for your patience. And I think if we go with some practical session, that will be better instead of theoretical session. Today we had much of theoretical session. Can we just reschedule? Like instead of KSCR, KSPR, these are actually commercial softwares to practice. So I'm going to teach you on molecular talking on tomorrow. Okay, and then we'll be discussing on molecular talking analysis. This is not energy information. I'll be taking you molecular talking analysis on the next day, including molecular dynamics simulation. Okay, later, the last day, I mean, we discuss on QACR because much of theoretical concept is there, so I can't able to interact you well. So tomorrow we have molecular talking session using Autodoc. I'll be circulating you the tool to download and install. Okay, so download and install the tools. It will be very useful for you. It's the most important method in drug design to check the binding affinity of a ligand binding with a receptor to check whether a drug is going to bind with a receptor to treat a disease or not. So join the session on tomorrow without fail. Okay then. Thank you. Have a great day to everyone. Bye. Good night.
Thank you, sir.